models were clear. Pluto reached the closest point to the Sun in its 248-year orbit back in 1989, and since then it has been moving steadily outward into the cold. As temperatures dropped, the nitrogen on its surface should have been freezing back out of the atmosphere. By the 2020s, the predictions said, most of the atmosphere should be gone, collapsed onto the surface as frost, leaving behind an airless rock in the outer solar system. James Webb Space Telescope looked at Pluto in 2023. The atmosphere was not gone. It was not even close to gone. And the infrared data Webb sent back contained something the models had not predicted at all. Evidence of a complex chemical cycle actively replenishing the atmosphere from below, suggesting that Pluto's interior is far more dynamic than a frozen, inert world has any business being. Pluto was discovered in 1930 by Clyde Tombaugh, and for 76 years it held planetary status while remaining almost entirely unknown. Even the best Earth-based telescopes resolved it as little more than a point of light. Its atmosphere was inferred in 1988, when Pluto passed in front of a distant star. The light from the star dimmed gradually rather than snapping off, which meant something gaseous surrounded the surface. That atmosphere is thin. At its peak, surface pressure on Pluto is roughly 10 to 25 microbars, about 100,000 times less than sea level pressure on Earth. It is composed primarily of nitrogen, with traces of methane and carbon monoxide. The same molecules that coat the surface as ices also exist in the gas phase, cycling between solid and vapor as temperatures shift. New Horizons changed everything in July 2015 when it flew through the Pluto system at 14 kilometers per second, the fastest spacecraft ever launched. The images it returned showed a world of unexpected complexity. A heart-shaped nitrogen glacier called Tombaugh Regio, covering an area larger than Texas and Oklahoma combined. Mountain ranges of water ice rising 3,500 meters above the plains. And, most striking, a layered blue haze extending 200 kilometers above the surface. That haze is made of tholins, complex organic molecules formed when sunlight and cosmic rays break apart nitrogen and methane in the upper atmosphere, and the fragments recombine into chains. On Earth, similar chemistry in a warm, wet environment is associated with the precursors of biological molecules. On Pluto, it creates a reddish-brown organic layer on the surface and a blue photochemical smog in the sky. After New Horizons, the outstanding question was, what happens next? Pluto was moving away from the Sun. The energy input driving the atmospheric chemistry was decreasing. Multiple teams used Earth-based stellar occultation measurements, watching Pluto pass in front of background stars to track atmospheric pressure over time. The results through 2018 showed the atmosphere still growing slightly, even though Pluto was getting colder. This was the first sign the models were incomplete. Then the occultation data through 2020 became ambiguous. And then Webb arrived. Webb's near-infrared spectrograph, NIRSpec, observed Pluto with a sensitivity no previous instrument could match at that distance. Pluto is 5.9 billion kilometers from Earth at its current position. Getting detailed spectroscopic data from an object that small and that far away was simply not possible before Webb. The first thing the data confirmed was that the atmosphere is substantially denser than the collapse models predicted for this point in Pluto's orbital cycle. The nitrogen atmosphere has not shut down. Pressure measurements derived from the infrared absorption features are consistent with readings from the late 2010s. The atmosphere is holding and possibly still evolving in ways that are not purely driven by solar distance. The second finding is more significant. Webb's spectrograph detected absorption features consistent with carbon monoxide and methane at higher altitudes than New Horizons measured in 2015. The vertical distribution of these molecules suggests upward transport, material moving from the surface or near-surface layers into the upper atmosphere at a rate that exceeds what simple sublimation from the sunlit nitrogen glacier would produce. The hypothesis this supports, the one that was considered speculative for years, is that Pluto has a subsurface reservoir of volatile material, possibly connected to a liquid water layer deep beneath the ice shell, and that geological or thermal processes are actively outgassing into the atmosphere. The idea of a subsurface ocean on Pluto was proposed based on the smoothness of Tombaugh Regio. A region that young, geologically speaking, should require heat from somewhere to resurface itself. Webb's atmospheric data provides independent evidence that something warm is operating below the surface. The carbon monoxide signal is particularly telling. CO has a short chemical lifetime in Pluto's atmosphere. It gets broken down by ultraviolet radiation relatively quickly. For it to be present at the concentrations Webb measured, at the altitudes observed, requires ongoing replenishment. Something is feeding it in. The most consistent explanation is active outgassing from interior reservoirs where CO is dissolved or trapped in subsurface ices or liquid. Pluto is not a colonization target in any near-term sense. It is 5.9 billion kilometers from Earth, takes over 4.5 hours for a radio signal to cross the distance one way, and sits in an environment where surface temperatures average -230 Celsius. Getting there with current propulsion technology takes roughly 9 years at the trajectory New Horizons used, and New Horizons was not carrying enough fuel to slow down and enter orbit. But the implications of a geologically active Pluto extend beyond the planet itself. Pluto is the largest and best-studied member of the Kuiper Belt, the ring of icy bodies beyond Neptune's orbit. If Pluto has a subsurface ocean sustained by radiogenic heating from its rocky core, then the same is likely true of other large Kuiper Belt objects: Eris, Makemake, Sedna. These bodies are far more numerous than the rocky planets of the inner solar system. The long-term vision of human expansion into the outer solar system depends on understanding where liquid water exists and where volatile molecules are accessible. An interior ocean on Pluto, continuously cycling material through the atmosphere, would mean that the outer solar system contains far more accessible chemistry than the frozen surface models suggested. For a civilization eventually building infrastructure at those distances, using Jupiter and Saturn as waypoints, the Kuiper Belt transitions from a cold, inert dead zone into something with resources worth cataloging. The tholins Webb detected in Pluto's atmosphere are also worth noting separately. These complex organic molecules are not unique to Pluto. They appear on Titan, on comets, in interstellar dust clouds. They represent the kind of pre-biological chemistry that forms wherever nitrogen, methane, and radiation interact. Understanding how they form and persist in Pluto's atmosphere adds to a broader map of where organic chemistry accumulates in the solar system. The subsurface ocean hypothesis is supported but not proven. Webb's atmospheric data is consistent with active outgassing, but the link to a liquid water interior is still inferred rather than directly observed. Confirming it would require a dedicated Pluto orbiter with seismometers and ground-penetrating radar, a mission that has been in various stages of proposal at NASA for years, but has not yet been approved or funded. The atmospheric pressure trajectory is also unresolved. The models predicted collapse. The observations show persistence. But it is not clear whether the atmosphere will stabilize at current levels, continue declining slowly, or eventually reach a new equilibrium driven by interior outgassing rather than solar energy input alone. Continued occultation monitoring from Earth and, where possible, additional Webb observations will be needed to distinguish between these scenarios. The tholin chemistry raises its own questions. The specific molecular pathways forming these compounds in Pluto's atmosphere are not fully characterized. Webb's spectroscopic data gives composition, but the kinetics, how fast the reactions proceed, what intermediate compounds form, how they sediment to the surface, require laboratory experiments designed to match Pluto's specific pressure and temperature conditions. And there is still the broader question of what Pluto's anomalous activity means for Kuiper Belt objects as a class. Are subsurface oceans common? Is Pluto the exception or the rule? The answer changes how we model the outer solar system and where we look next. For most of the time since its discovery, Pluto was treated as a footnote. First demoted from planet to dwarf planet in 2006, then effectively ignored as a destination because it was assumed to be geologically dead and atmospherically simple. The models said the air would freeze. The models said there was nothing dynamic to study. New Horizons showed the surface was wrong. Webb is now showing the atmosphere is wrong too. A world at the edge of the solar system, -230 degrees Celsius on the surface, 5.9 billion kilometers from the sun. and something inside it is still running, still outgassing, still feeding a chemistry that should not be active at those temperatures and that distance. The crazy hypothesis was that Pluto is not dead. Webb just confirmed it.